Hello, everyone. I'm going to continue today my inquiry into the fraught realm, let's say, of climate science, the so-called settled climate science. I'm talking today to Dr. Richard Lindzen. He's an accomplished professor, atmospheric physicist, and meteorologist, having authored over 200 scientific papers and contributed to landmark theories in the realm of ozone photochemistry, atmospheric tides, and most recently, climate stability. Holding a rare view in opposition to mainstream science, or perhaps not so rare, Lindzen disagrees on the role of water vapor in current climate change models and argues that alarmism is widespread, aided by political consensus, not unlike the once popular research on eugenics. Dr. Richard Lindzen is a dynamical meteorologist. He has contributed to the development of theories for the Hadley circulation, hydrodynamic instability theory, internal gravity waves, atmospheric tides, and the quasi-biennial oscillation of the stratosphere. His current research is focused on climate sensitivity, the role of cirrus clouds in climate, and the determination of the tropics to pole temperature difference. His academic degrees are all from Harvard University. He is the recipient of various awards and is a member of the National Academy of Sciences and a fellow of the American Academy of Arts and Sciences, the American Geophysical Union, the American Meteorological Society, and the American Association for the Advancement of Science. Between 1983 and 2013, he was the Alfred P. Sloan Professor of Atmospheric Sciences at MIT. He assumed emeritus status as of July of 2013. Prior to 1983, he held professorships at the University of Chicago and Harvard University. He's also been a distinguished visiting scientist at the Jet Propulsion Laboratory, as well as a visiting professor at the Hebrew University, Tel Aviv University, the École Normale Supérieure, the University of Paris, and Kyushu University. The first thing we're going to determine before we dive into the topic at hand is why it might be reasonable and important to listen to Dr. Lindzen. So we're going to go through his academic background and then we'll proceed to the main issue. So you did your undergraduate degree at Harvard, and
yeah.
if that's right, in physics from 1960. Let's start from there.
Okay, yeah. I graduated from Harvard in physics 1960, so it was a long time ago. I realized at that point that I really enjoyed classical physics, and actually modern physics seemed in some ways intimidating. So I continued in graduate work in applied mathematics. Now, Harvard was different from other places in applied math. Places like NYU were very heavy into the theoretical aspects of applied math. Harvard applied math was solving problems with applied math, and they were heavily into problems in meteorology and other things. And so I ended up doing a thesis that was really atmospheric physics. It was the interaction of fluid motions and chemistry and radiative transfer, mostly in the stratosphere. And there were a lot of good problems. I enjoyed it. The one problem with it was there was very little experience with data. And so I went for a postdoctoral period at the University of Washington, and there was a superb data analyst, Dick Reed, who was on the faculty there. He's now deceased. And after that, I went to Norway for a year, and there was a very able and famous dynamic meteorologist there, Arnta Eliassen. And that was also a pleasure. And during that time, I began working on some other problems, ranging from tides in the atmosphere to some problem called the quasi-biennial oscillation. You may not realize it, but the wind over the equator at about 15 kilometers roughly, plus or minus 10, goes from east to west for 1 year turns around, goes the other way for another year. The average period is actually about 26 months. And that had been a puzzle. And we managed to find a solution to that puzzle as to how that worked. Probably too complicated to explain. It involves, random waves generated by the cumulus clouds in the tropics interacting with the flow and forming something that essentially would be called a relaxation oscillator. And that's actually held up pretty well for almost 50 years or 60 years. So as theories go, that did well. There was also a problem with tides. I mean, people familiar with tides in the ocean know that they're primarily 12-hour lunar tides. And they're lunar tides because the moon, although much less massive than the sun, is so close that its perturbation to the gravitational potential is greater than that of the sun. But then it was observed that in the pressure at the surface in the Earth, the tides were also primarily semi-diurnal, that is, say, 12 hours, but solar. And so that was a bit of a puzzle because that had to be thermal. And Lord Kelvin in the 19th century was asking, given that the 24-hour component was much stronger, why was it 12 hours? And he suggested the atmosphere was resonant at 12 hours. And that actually dominated the literature until the late 50s.
Resonant meaning what?
Meaning, let's say you have a violin or something. You stroke and you get a certain note. That's because it's resonant at that note. It displays that.
Vibrates at that note.
And so people had figured out, how it might be resonant and so on. But after World War II, when one had rockets, one realized the atmosphere was not the way it had to be resonant. And we figured out why the 24-hour got trapped. And so that was kind of fun. There's problems like that make, in some ways, atmospheric science, meteorology, geology, geophysics, kind of fun. They're great fields.
So you liked physics a little bit more on the concrete side, a little bit more data driven, a little bit more down to earth than the theoretical realm. And then, so you said you were at Washington to do a postdoc, and then you went to Norway. What happened after that?
And then I went to the National Center for Atmospheric Research, and I was a staff scientist there. And there was a sort of reason for it. It was slightly cynical. Some of my classmates had gone into academia, and I was watching it. What a horror show being an assistant professor was. You had insecurity, you had a heavy teaching load, you didn't have time to do the research. So I decided I would stay at a research center until I was offered tenure. And I was, after a couple of years, offered a tenure post at the University of Chicago. And that was a very nice experience. I loved Chicago. But my wife was a little bit insecure about the crime situation on the south side of Chicago. And when Harvard made an offer of a chair, we accepted it. I left Chicago. And we came to Harvard, and I spent about 10 years there as I think, eventually, I was first the Gordon McKay professor, then there was some other chair. But I had a close colleague at MIT, Jewel Charney, who was a preeminent dynamic meteorologist, but also a very interesting guy, good friend. And he died, and I was offered his chair at MIT. and I took
When
it.
was that?
That had to be the early 80s.
Okay, so I should just point out for everyone who's watching and listening that this is a pretty, what would you call it, stellar academic track. So first of all, an undergraduate at Harvard, and then applied PhD work at the postdoc level in a variety of different places, including research institutions. But the fact that Dr. Lindzen was offered tenure at U Chicago, a tenured position to begin with, that's not the normal mode of making an entry way into academia. Usually you start as an assistant professor, and so that's untenured. And it's very rare to be offered a first-time job as a tenured professor. Was that associate level or full professor?
That was associate. I wasn't promoted
Okay,
until a few years later.
Right, and then, okay, so from the University of Chicago, then you were offered a Harvard chair, and I want to point out to everyone who's watching and listening again that that's very rare. So at Harvard, the hiring streams are really broken into two segments. And so you have faculty members who are hired as assistant professors, so that's the most junior level of professor. And those positions are not tenured at the Ivy Leagues, generally speaking. And so what the Ivy Leagues do is bring in promising young people at the assistant level, but turn them over. And that gives lots of people a chance to work at the Ivy Leagues, and it gives the students a chance to be in contact with dynamic young researchers, let's say. But the second hiring stream, and the more important one, is the senior professors, and that's usually at associate or full professor level. And what Harvard did when I was there, that was in the 90s, was, and I'm sure the practice still continues and is characteristic of Ivies in general, is they look all over the world for the people who are doing the top research in their areas at a relatively senior level, and then make them an offer, see if they can entice them to come to Harvard. And so that doesn't happen to very many people. It's a very, very rare occurrence. It's not that huge a university, Harvard, and there aren't that many professorships. So to be offered a chair there is, well, it's a mark of, I would say, universal esteem directed towards a given professor within the confines of their research. And they have to have made quite a splash on the research front for that to happen. And then to move from Harvard to MIT, well, the same thing is the case there because, well, Harvard and MIT battle it out for priority, let's say, for the most prestigious and highest quality university in the US and possibly in the world. You could have an argument about that. But to move from Harvard to MIT is well, that's another indication of a stellar academic career. So you went to MIT in the 1980s.
Yeah.
And you were there until you retired?
Yeah, till I retired formally in 2013. But, they've been good to me. I have an office and, some assistants occasionally. And, of course, one of the things is you no longer have students. Well, that's a bit of a drawback. I occasionally, however, have colleagues. And even, at the end of it, for reasons that are obvious, I had almost no funding, but there were some postdocs who paid their way from South Korea, so that was helpful.
So did you have a preference for Harvard or MIT in terms of the students you encountered?
Not really. I mean, the students I encountered changed over time more than they changed with place. When I came to Harvard, the students in my area were, I would say, in some ways coming from math and physics, mostly. They were the overflow, and there were lots of kids studying math and physics. So they were good, and very good, in fact. And that was sort of true when I came to MIT. But by the 90s, things changed a little bit. First of all, good students were not entering physics and math at the level that they had once did. The best students often were going into finance, things like that.
Right.
And so there was no overflow. And I think there was a slight change in the nature of students. They were not as theoretical. They were more model-oriented and so on. There was also a change at MIT, which was not something we wanted, which is it was getting harder and harder to find people working with data. And so the students were getting less experience with actual data. But those are changes. I mean, compared to current changes, they probably were minor. I mean, at the moment,
Right.
I just find it strange. There's so much emphasis on racism in the earth sciences and so on. I'm sort of glad I'm not teaching at this point.
Yeah. Well, it's that one-trick pony, that ideological insistence that something approximating critical race theory should dominate every single discipline. And it gives people who really have no background whatsoever in these fields the opportunity to dominate. And it's really quite an appalling thing to see.
Yeah, we'll see one other
well,
thing, too, which is the vast increase in both numbers, power, and importance of administrators.
Yes, definitely. Yeah.
I mean,
Yeah, well, it's I think in some ways we live inside a giant whale carcass that's walking on the beach. And well, really, it's a good biological metaphor. And there's plenty of food for everyone for a very short period of time. And the administrative overload in the university is something remarkable to behold, especially because it's been built on the backs of students and their student loan.
Oh yeah, but it's
like
not
indentured servitude, I would say.
It's more than that. It's you now have administrators certainly outnumbering faculty, and in many places outnumbering faculty and students. And they need money, but they do not do the functions that the university gets paid for: teaching, research, and so on. And so we have overhead on the grants, and that has become critically important. The more overhead, the better the administration likes you. So, if you have a big laboratory, you'll have more overhead than someone who does theory. And if you're a
Well, when I was there, we were paying about 50% in overhead costs, if I remember correctly, for a given grant. So scientists spent about a third of their time in the United States. It's one of the reasons I was actually happy to come back to Canada. Is the scientists I knew in the U.S. were spending 1/3 of their time
writing proposals,
taking a shot at about a 5% chance at getting a large grant, and 50% of that went to overhead. It was quite the waste of time for the scientific community, because that meant, the brightest people in our community were spending 30% of their time at least writing grants that had a pretty low probability of success.
Yeah.
Instead of, and then, of course, that the problem with writing grants is that you tend to have to study trendy topics, and you also can't be very daring. You have to take the next obvious step in some real sense, and only in the approved direction. And so that whole granting system to me looked like something approximating the death of exploratory science.
Well, that actually also evolved over time. When I entered academia, the National Science Foundation actually had very few staff. And they were eager to give out money. There wasn't that much demand for it.
Right.
But as the administration grew, there was also, the administration plays a large role in the behavior of departments. Young faculty today, are sunk if they don't get grants.
Oh, yeah.
And when we get to climate, you don't get grants if you question the current narrative.
Let's delve into that a bit. When you were at MIT and at Harvard, how many papers have you published approximately, you and your colleagues?
250 or so.
Okay, so for those of you who are watching and listening, and correct me if you think I'm making an error proposition here. So when I was working as a faculty member, we kind of had a rule of thumb in the psychology department, which was that if a student prepared 3 publishable papers that were sequentially linked, added an introduction to that and a conclusion, we would basically accept that as a thesis. And so the rough equivalence was 3 published papers equals a PhD thesis. And you've published 250 papers, so in some real sense, that's equivalent to 80 PhDs. Now, what do you think of that for a line of logic?
Not much, but to be honest.
Okay, so, I'm trying to give everyone watching and listening a sense, because people don't really know what it means to have a publication record like that, eh?
Well, I mean...
So that's what I'm trying to elucidate.
Yeah, I think it's also a matter that has changed with time. I mean, people like, Jewel Charney, who I mentioned, who is the leading figure in dynamic meteorology, probably published 60 papers. Arndt Eliasson, who was also a terrific influence, something that order. The pressures to publish have increased. And so people's behavior is different. Also, publication has become a very different issue. You probably know that before World War II, peer review was very rare. And if I have students read papers from the 19th century or the early 20th century, they're quite surprised to read them. Why? Because they're informal. They're communications. They're not assertions of truth. They are looking for truth. After the war, for a variety of reasons, peer review entered, largely because there was too much demand for publication. May even have been a shortage of paper. But, for instance, the Quarterly Journal of the Royal Meteorological Society in the UK had a wonderful statement of what the reviewer was supposed to do. And it said, you can only reject a paper for 2 reasons. One is an overt mathematical error or lack of originality. The paper then would be discussed at the monthly meeting, and the discussion would be included with the paper. There was no essential thought that peer review, the public has been made to think that this is a certification of the paper, that it is somehow proven right.
Now it's fact, right.
Yeah, and it's nothing of the sort. It is to see if the stuff is interesting and it's not overtly wrong mathematically and not plagiarized. On the other hand, it's become something more. I mentioned, I had 2 papers that appeared in the Bulletin of the American Meteorological Society that dealt with climate and my objections to the current narrative in various ways. And they got published, they got reviewed, but in both cases, the editor was fired immediately. And
that's cute. That was when?
Well,
when did that happen?
One was 2000. One was 1991 or 2, and the other one was.
So you were on this early.
Oh, well, this issue actually began in the 60s.
Mm-hmm, right.
And it was clear there was a lot of hunting around for some environmental issue that would give people power on the over the energy sector. And so, you had Earth Day in the early 60s, but then you had global cooling, and the villain there was...
That was the 70s,
Yeah, well, it was 60s and 70s, and continued to the 70s. And the notion there is you wanted to get rid of coal-fired plants because they were polluting and creating sulfates that were reflecting light and causing global cooling. You also had acid rain at that time.
Yeah.
And again, get rid of the energy sector. And both of those turn out to be duds. And this global mean temperature metric, whatever it is, started increasing in the 70s. So they said, well, this won't go. And for a number of reasons, CO2 came into the issue. One of the reasons was the International Geophysical Year began a measurement program for CO2 at Mauna Loa Observatory in Hawaii. And this was Charles Keeling, and it was promoted by a man called Roger Revelle, who was director at Scripps, which is an oceanographic institution in California. At any rate, they noticed CO2 has been increasing. And the evidence is it's been increasing since the industrial era began, but serious levels, at least measurable, were being reached in the 50s, 60s, where it was perhaps significant in terms of heating.
Mm-hmm. Why did they start measuring it?
Well, curiosity.
Yeah, okay.
I mean,
so they were just curious to begin with.
Yeah. I mean, it's an interesting chemical. It plays a role in photosynthesis. It's vital. We have, like 40,000 parts per million in our breath. So, it's an interesting substance. And part of the reason it's interesting is, of course, that it has infrared absorption, and so it plays a role in what is called the greenhouse effect. Okay, so they found it, and the question then was, what are the implications? But more than that, if you were interested in controlling the energy sector, is the fact that no matter how clean you made the burning of fossil fuels, you would inevitably be left with the product of clean burning, which was CO2.
I see. So this was one...
You couldn't get rid of it.
Pollutant. I see. So
not a
matter how
pollutant.
clean the fossil fuel energy became, they were never going to get rid of carbon dioxide.
Just like...
So that was a good... Now, why do you think there was attempts to... You talked about control of the energy sector. Why bring that into it?
Well, I mean, your guess is as good as mine, but it obviously is at the heart of industrial development. It's the heart of the prosperity of the West. You had all these Malthusian movements, Paul Ehrlich, John Holdren, zero population growth. And, you see now, a kind of antipathy to the working middle class. You begin to feel there were people who resented the fact that ordinary people were aspiring to live decently, have a car, own a house. And for some reason, I think that...
warm?
Yeah, right. Have a dishwasher. And I don't know why, but there is almost an antipathy to this.
I was talking to Alex Epstein recently. He wrote a book called Fossil Fuel.
Oh, yeah.
He attempted to lay out some of the, you might think, theological or metaphysical presuppositions underlying this. And, your comment on envy is an interesting one, that, there's some antipathy towards having ordinary people thrive, which is a pretty nasty form of antipathy. His point was that I guess there were two, one on the Malthusian front and one on the more quasi-religious front, is that there's an idea that the only acceptable natural landscape in some real sense is one that's been completely untouched by human beings. And so if that's your presupposition to begin with, then anything that has to do with industry is going to be, let's say, persona non grata. And then if you combine that with this Malthusian notion, which we could go into a little bit. So the Malthusian notion, for everyone watching and listening, is It's based on something like a Petri dish model. So a Petri dish is an enclosed plastic container that has a medium in it, often agar, which is a kind of gelatin that you can grow microorganisms on. And if you throw a microorganism in there, it'll start to multiply until it eats up all of the agar, and then it'll all die. And so there's this idea that's in some sense a biological idea that populations left to their own devices will multiply until they devour all their resources, and then they will perish en masse. And the Malthusian predictions of population collapse that started to emerge in the 60s were based on this Petri dish model in some real sense. And the problem with that model is that it isn't obvious that single-celled organisms are a good metaphor for human beings, because we're capable of extremely radical adaptation and transformation, whereas single-celled organisms just basically run out something like an algorithmic program, even though they're quite complex. And so the notion that human populations are destined to a Malthusian end is not, what would you call it? It is not a canonical biological fact. Let's put it that way.
Well,
but it's certainly driving a lot of this sort of thing we're talking about.
Yeah, I mean, it's a little bit tricky in a sense what motivates people. It's clear that at the top, they have no interest in restricting their own consumption. It's also very much, I mean, you know, when you try and figure out what's the right population, I guess in some sense you could say there must be some limit, but, you know, you look at India in my lifetime. I mean, before independence and even shortly after, its population was under 200 million, and famine was common. And today it's 1.3 billion, and they're food exporters.
Right, right. Yeah, I just saw a chart the other day too that showed that over about the last 10 years, a fair bit of farmland has been taken out of production, and some of that's reverted to the wild. And yet, despite there being less farmland being used now, the amount of food that the world is producing is still increasing at a pretty damn rapid rate. And so it isn't obvious at all what the upper bound is for population capacity.
Oh, yeah. I mean, you know, agriculture has become far more efficient. And, you know, this leads to this peculiar emphasis on food that has not used fertilizer and so on, you know, which would lead...
like that's going to... we're not at that point yet.
That would lead to starvation.
Without ammonia, it's 4 billion people would die without ammonia fertilizer. That's the estimates at the moment.
Yeah, I mean, so everything about this is sort of nuts. Alex Epstein, who you mentioned, has, you know, pointed this out, but it's kind of obvious. I've noted this. I mean, you could do everything, you know, bury Europe, bury the US, Canada, get rid of all their emissions, period. All dead and buried. And it would make very little difference to the growth of CO2, since most of the world is not this stupid as to commit suicide. Right. And so if you really believe the cataclysmic claims, which have no scientific basis, but let's say they're true, you're doing nothing to stop it. On the contrary, you're impoverishing your societies and making them less resilient. Because if you think natural disasters are coming, where would you rather be today? Haiti, or in Chicago, or New York, or Los Angeles?
Well, it's also the case. It's also the case that I don't see any evidence at all, because you could make a case, arguably, if you believe the carbon dioxide climate catastrophe narrative, you could make a case that it's ethically required to impoverish people if you could demonstrate that that impoverishment actually produced, let's say, a decrease in carbon output. But that certainly isn't what's happened in Germany, since Germany's gone madly green. In fact, their their energy production is much less efficient than it was 10 years ago, and it's 5 times as expensive, and it pollutes far more.
Yeah.
And so my sense is that, and I think the data bear this out too, is that if you provided people with cheap, clean energy on a world basis and eradicated absolute poverty, or at least ameliorated to the degree that was possible, then people start caring about the long term, and they start working for environmental preservation at a local level. And that's a far more effective way of taking care of the planet. So not only do you impoverish people and make the planet worse. And as far as I can tell, that's just essentially unforgivable. So why do you think, so 2 things, we left something hanging. You said 2 editors got fired, one in 1992. When was the second one who got fired for publishing something you wrote?
2001. It was immediate.
2001. Okay. And so now, when you started to object to the narrative, what narrative were you objecting to, and on what grounds? This is back, say, in 92. What narrative were you objecting to, and on what grounds were you objecting
You're
to?
touching on something that took me a while to understand. Goebbels famously said, if you tell a big enough lie and repeat it often enough, it'll become the truth. There's been a lot of that in this, but there are aspects of establishing the narrative, i.e. what makes something the truth, that I hadn't appreciated. So the narrative was the climate is determined by a greenhouse effect, and adding CO2 to it increases it, causes warming, and moreover, the natural greenhouse substances besides CO2, water vapor, clouds, upper-level clouds, will amplify whatever man does. Now, that immediately goes against Le Chatelier's principle, which says if you perturb a system and it is capable internally of counteracting it, it will. And our system is.
And you think that applies? Okay, and so that's a very germane issue, because...
Well, but let me...
Even if please go ahead.
Let me finish, because, okay, so that was a little bit odd. You began wondering, where did these feedbacks come from? And immediately, people, including myself, started looking into the feedbacks and seeing whether there were any negative ones or how did it work. But underlying it, and this is what I learned, if you want to get a narrative established, the crucial thing is to pepper it with errors, questionable things, so that the critics will seize on that and not question the basic narrative. The basic narrative in this sense was that climate is controlled by the greenhouse effect. In point of fact, the Earth's climate system, which has many regions, but 2 distinct different regions are the tropics, roughly the minus 30 to 30 degrees latitude, and the extratropics, outside of 30 degrees, plus or minus. They have very different dynamics. In the tropics, the crucial thing for the Earth, by the way, and this is a technicality and much harder to convey than saying that greenhouse gases are a blanket or that 97% of scientists agree. This is actually a technical issue. The Earth rotates. Now, people are aware of that. We have day and night. But there is something called the Coriolis effect. When you're on a rotating system, it gives rise to the appearance of forces that change the winds relative to the rotation. And the only component of the rotation is the component that is perpendicular to the surface. So at the pole, the rotation vector is perpendicular to the surface. At the equator, it's parallel to the surface. It's 0. And this gives you phenomenally different dynamics. So where you don't have a vertical component to the rotation vector, motions do what they do in the laboratory in small scales. If you have a temperature difference, it acts to wipe it out. And so if you look at the tropics, the temperatures at any surface are relatively flat. They don't vary much with latitude. On the other hand, you go to the mid-latitudes, extratropics, there the temperature varies a lot between the tropics and the pole. We know that. I mean, temperatures are cold at high latitudes. And if you look at changes in climate in the Earth's history, what they consist in is a tropics that stays relatively constant. And what changes is the temperature difference between the tropics and the pole. During the Ice Age, it was about 40 degrees centigrade. Today it was about 60. Today it's about 40. During 50 million years ago, something called the Eocene was about 20. And so that's all a function of what's going on outside the tropics. Within the tropics, the greenhouse effect is significant. But what determines the temperature change between the tropics and the pole has very little to do with the greenhouse effect. It is a dynamic phenomenon based on the fact that if you have a temperature difference with latitude, it generates instabilities. These instabilities take the form of the cyclonic and anticyclonic patterns that you see on the weather map. Now, the tropics are very different. I mean, even a casual look at a weather map, the systems that bring us weather travel from west to east at latitudes outside the tropics. Within the tropics, they travel from east to west. The prevailing winds are opposite in the two sections. And we're saying that what changes due to the greenhouse effect, however you look at it, is amplified at the poles. That is not true. There's no physical basis for that statement. All they do is determine the starting point for where the temperature changes in mid-latitudes, and that's determined mainly by hydrodynamics. Okay, that's complicated to explain to someone. Mm-hmm. And yet, it's the basis for claiming that these seemingly small numbers, they're saying if global mean temperature goes up 1.5 degrees, it's the end. That's based on it getting much bigger at high latitudes and determining that. But all 1.5 degrees at the equator would do, or in the greenhouse part of the Earth, is change the temperature everywhere by 1.5 degrees, which for most of us is less than the temperature change between breakfast and lunch. And the thought that this is the end of the world is a little bit crazy.
All right, so let's play devil's advocate here for a minute. And so let me lay out the narrative and correct me if I've got it wrong. So first of all, the world at the moment is making a big deal out of climate and associating climate change with the greenhouse effect, the trapping of heat. Mm-hmm. And we're all associating the greenhouse effect with an increase in carbon dioxide. And at least initially, we were associating that increase in carbon dioxide with global warming. Mm-hmm. And then we've added the proposition that, well, not only will there be warming, say, of up to 1.5 degrees or 2 degrees by the end of the century, and maybe there's some variation in those predictions, but we're also looking at a system that's characterized by a variety of positive feedback loops. And the danger here is that a 1.5 degree increase might not be catastrophic, but that might trigger a sequence of cataclysmic events. We hear sometimes about the melting of the Greenland ice cap, for example, the rapid rise in sea level that would occur as a consequence, the increase of temperatures at the poles, the release of methane as a consequence, let's say, of the permafrost thawing, and then a runaway greenhouse effect because of that. And you evinced some skepticism, about the whole narrative, but also more particularly, and perhaps more importantly, you don't sound like you're a big fan of the idea of runaway positive feedback loops.
Oh, well, there are a lot of things enmeshed in what you've said. Even the 1.5 degree depends on the positive feedbacks. Otherwise, CO2 would be even less significant, much less significant. So those, you assume that water vapor increases and amplifies it, but the whole picture is one-dimensional. So, you'd have to know the area where water vapor is important. It goes through a mess of things. And we know now that that probably isn't occurring, even people who support the narrative. So you keep
that water vapor isn't amplifying carbon dioxide effects.
If it is, it has to be considered as part of an infrared feedback, and nobody has detected that that is actually positive.
Okay. Well, I read that the putative contribution of carbon dioxide to global warming is less than the margin of error for measurement of the effect of water vapor.
Yeah.
Do you know if that's true? That's really sad if that's true.
That's true.
Really sad if that's true.
It is true if you want to measure it rather than hypothesize it. Then what you're saying is true. It's been hypothesized. In other words,
so we're planning on spending $2 trillion to remediate a problem whose magnitude is so small that it could easily be hidden within another measurement error on the water vapor front.
I think so. But I mean,
boy, that's really quite something.
No, I mean, it's caught the fancy of the political world. I mean, I'll give you an example of it. We're falling into the trap I mentioned, going along with the narrative because it has so many weaknesses, ignores the fact that the whole picture of the greenhouse is misconceived.
Okay, well, let's not go too far down that rabbit hole because I'd like to stay focused on critique of the major narrative.
Yeah, no, I mean, I'm quite willing to talk about the other problems.
Yeah.
But the fact that you don't have this polar amplification, that it's going to be bigger at high latitudes, it may be, but it's not due to the greenhouse. It's due to processes in the extratropics where the greenhouse is secondary by a long shot. There's one example of what you're saying, and it helps, I think, understand why this issue gets so distorted. In one of the International Panel on Climate Change, this UN body, reports, I think the third report, somewhere in the early 2000s, where I was a lead author, but that we can get to that later. But in any case, they have this 1,000 pages that deals with the science, has no index, is totally unreadable. Mm-hmm. And then they have a summary for policymakers, which isn't really due to the scientists, and they can manipulate the text because that comes out 6 months before the text of which it's a summary. But, they know people aren't even going to read that. So you have the 1,000 pages they're not going to read, then you have 20 pages they're not going to read. And so you have the press release. And the press release is the iconic statement, and that's what gets the headlines. So the iconic statement was they now are, I forget how certain, that most of the warming since 1960 is due to man. Okay. In truth, that doesn't mean much. It was about 0.5 degree. It was most consistent with the climate being relatively insensitive. It was basically a statement, there's not much of a problem here. But they didn't say that. They just said most of the warming since 1960 is due to man. All of a sudden...
What does most mean? Does most mean 95% or 51%?
Could mean 51%.
Yeah, okay.
Even if it meant 100%, it wouldn't matter. It was small.
Yeah, got it.
But how did Senators McCain and Lieberman respond to that? They come out immediately with a statement, this is the smoking gun, we must do something. So as long as the scientists can make innocent remarks and be assured that politicians will convert them into alarm and increase funding, why are they going to complain? And so you have this insidious interaction where scientists, and there's another guy, Steve Koonin, who's written this book, and I know Steve well, and the point is he could use the documents that are cited on behalf of alarm to say, look, nobody here is saying it's the problem that the environmentalists and the politicians are saying. Where did this come from? Right. And the answer is it came...
well, Bjorn Lomborg has done the same thing.
Right.
I mean, he accepts the IPCC predictions, essentially, with some criticism, but says, look, well, if they're right, this is straight from the horse's mouth, let's say, with regard to the UN, even if they're correct, that'll mean two things. The first is we'll be slightly less rich than we would have been 100 years from now because economic growth is so high, and we won't even notice that in some real sense. But even if it's slightly bigger than we predict, we're so good at adapting, and you can see, like the curves, for example, in terms of number of people who are dying from natural disasters each year, which has declined precipitously over 100 years. We're so good at adapting that the probability that we can just adapt to this is 100%. Now that, of course, that assumes that there are none of these runaway positive feedback loop effects. But my problem with that on the scientific front was, well, how the hell do you predict a runaway positive feedback loop? You can't predict that as far as I can tell.
By the way, the feedbacks are not runaways that they're using. They just amplify. You'd have to get a much higher level of feedback to be a runaway system. The tipping point is a different argument. And I find that kind of nutty because tipping points in the climate system are virtually unheard of. And there's a good reason for it. They're usually characteristic of systems that have what I would call few degrees of freedom. So, for instance, so it's saying if you want to make a transition from one state to another, you don't have many places to go, so it has to take a leap.
Oh, right. Oh, I see what you mean. So a system that's constrained in its modes of possibility tip, because there's only a couple of states it can be in, but a complex system can be multiple.
But a system like ours
that's very good.
Has an infinite number of degrees of freedom, essentially, and it can go smoothly through anything.
Okay, has that proposition been quantified? Like, I've never heard that before. It makes a lot of sense to me that, a system that flips would flip because it could be frozen or liquid, let's say, in the case of water. But a system that's complex and highly entropic, because of that, has many, many ways of dispensing, let's say, with extra energy.
Yeah, so-called degrees of freedom.
It looks like a formal argument.
Yeah, I haven't seen it explicitly expressed, but I'm pretty sure there's something in the literature about that.
Well, it makes sense if a system has multiple ways of dispersing with increased energy input. Then it's not going to. The probability that it's going to do something dramatic has got to be proportionate in some sense to the number of options that it has.
I mean, look, the number. As I was saying, if you want to pepper something with craziness, this issue has a lot to speak of on that count. I mean, one of the ones I like is this metric for climate, which is a very peculiar metric, some global temperature.
Yeah.
What is it?
Global mean.
What is it? How do you get it? Where is it? I mean, how do you take the temperature of the Earth?
Let's walk into that. Some of that, so some of that is a consequence of many, many weather stations distributed on the physical surface of the Earth. But the problem with those is that many of them were built in places where urban encroachment has expanded over 100 years. And so that's a huge problem on the measurement front.
Yeah, but that's sophisticated. How do you average Mount Everest with the Dead Sea?
Well, I'm curious about that. How is that done? Like to think of the Earth as having one temperature.
Yeah.
You're making the case there that the mean is the crucial variable, right? That's really what it boils down to.
Well, it's saying that, but it's hard to tell how you get it. They don't get it, by the way, by averaging. What they do...
Okay, well, how else can you get it?
Okay. What they do is take each station, take a 30-year average, I forget, it's, like 1950 to 1980 or something, and look at the deviation of the temperature from that average. And they average the anomalies, the deviation. Okay? So, let's say it went up 3 degrees at one station from the 30-year mean, went up 2 and 1 and so on. They average those numbers instead of the temperature itself.
Okay, why? And who's they?
The British Met Office, NOAA, NASA, so on. Everyone producing a temperature record is doing that. Okay. Maybe it makes sense, because you don't want to average Mount Everest and the Dead Sea, but maybe the changes in temperature at those places you could average and get an average temperature change. Okay, so you do that. And they show you the graph, but they never show you the data points. And if you show the data points, and this is a guy at Lawrence Livermore Laboratory who did this around 1990, he died in 92. He showed the data points. And whereas this global mean temperature record is changing a degree and a half over a century and a half, the data points are scattered over 20 degrees.
Right.
And they're densely scattered.
Huge error.
Not error. There's just huge range.
Just scatter.
And if you chose any given period of time, any moment, there are almost as many stations cooling as warming, even though the trend is slightly warming, because it's slight. And so when you see somebody at a given location saying, this is a cold day, how come they say it's warming? Well, the data says it could almost be as likely to cool as warm, except there's a slight bias. And it's, when you look at the media, if there's an extreme at any given place, they say it's climate. But the data, doesn't suggest that.
Okay, so part of the problem here is that we have a single measure, which is this average change in temperature. Now that's become the standard for assessing something like global planetary health.
Oh, yeah.
And now our entire industrial enterprise is being bent to serve that particular master. So what do you think's wrong with the average mean temperature as a univariate variable? I mean, you talked about scatter, so that's a problem, but apart from scatter...
The other problem with it is, and it explains why, for instance, textbooks on climate from the 40s through the 60s didn't discuss this metric. They discussed the fact that the Earth had many climate regimes, dozens. And they wanted to know what accounted for the different regimes of climate on the Earth, something called Köppen classification. This metric became popular with global cooling, global warming, and so on, because you wanted to have something singular that showed one or the other. I think they were capitalizing also on the fact that as a British physicist and novelist, C.P. Snow, realized many years ago, that we have two cultures. Well, I think we have more than that. Or maybe we have no cultures. But if you're not a scientist, it is amazing how innumerate and illiterate you can be. And so...
Or even if you are a scientist.
Yeah, but there's a different kind of ignorance, specialization and so on. But most people looking at a graph can't read a graph.
Right.
And so, if you look at the financial page, people, see the same graph. If it went up 10 points and went up 100 points and went up 200 points, all they see is it went up. And they rescale and they show you that. Because if they only show you something that is objective, some days it wouldn't look like it's doing anything. And so
what would you regard as the major drivers of? Look, okay, let's go back even a step further. Do you think that we have any real existential concerns on the climate front?
Not for the next 5,000 years.
Okay. So we probably don't have to worry about that for at least 4,000 years.
I think so. And we would see it. I mean, it's, we had these massive ice ages and every roughly 100,000 years. And the glacial part of it is longer than the interglacial that we're in now. So, but we're talking about scales of thousands of years for that. That's a major change. And it was understood by a Serbian astronomer in the 1930s, early 40s, that this was largely due to the orbital variations of the Earth, which produced changes in solar radiation incident on the Earth in summer in the Arctic of 100 watts per meter squared. Remember, with CO2, you're talking about 2 watts per meter squared, 3 watts per meter, 1.5 between the ice ages, 100. And why summer in the Arctic? Because you always have snow in the winter in the Arctic. The question is how much of it survives the summer. If it's cold during the summer, the snow lasts and builds up on a new base each year. And over thousands of years becomes a kilometer or two of ice over you. On the other hand, if the summers are warm, the snow doesn't last and you don't build your ice.
Okay, so the main drivers of that kind of
that was orbital
cataclysmic change, that's orbital. And those are, you said 100 watts per square meter.
Right.
Essentially. And now you're pointing out that the putative effect of carbon dioxide warming is something like 2 watts per meter.
That order.
And that's going to produce a comparatively small perturbation, nothing of the order of magnitude that's associated, say, with glaciation or the lack thereof.
Yeah,
and also not an amount that'll produce positive feedback loops. Of great magnitude.
Producing positive feedback loops, I think, is a kind of funny phrasing. The feedback loops are intrinsic to the system. And the question is, do we have positive feedback loops? And I don't think so. Not really serious ones.
Okay.
And yet they're assumed in order to get a big bang out of the CO2.
Yeah, okay, so on what basis are they assumed? Because you already made the case of degrees of freedom. So what's going on here scientifically? How can that story be put forward with any degree of credibility?
By saying it's credible. I mean, that's what we're doing. I mean, in other words, Suki Minabe did some papers in the early 70s where he assumed essentially one-dimensionality for the system, no clouds, no nothing. And he said, if I assume relative humidity remains fixed, and I have no clouds, or I don't let clouds change, then, because of something called the Clausius-Clapeyron relation, the warmer it gets, the more moisture the atmosphere can hold. And if the relative humidity is fixed, you'll have more moisture. Okay, and he showed you could get a doubling of the effect of CO2 from that. It just happens to only apply in the tropics, and it is not, the clouds are not fixed. They are also changing and counteracting, I think, much of what's happening due to the water vapor, and changing the area over which the water vapor acts. So it's a much more complicated affair. And the measurements from satellites are suggesting that the whole shebang, when put together, is not producing the feedback that you needed to double the effect.
You've expressed a lot of skepticism about computer models. Now, when the average person reads that a computer model makes a given prediction, especially if it's reported in a peer-reviewed paper, they're inclined to presume that that means two things. It means data and it means fact. But I'm very skeptical of computer models because you have to make all sorts of assumptions, and the devil's in the details with something as complex as climate. So on what grounds have you gone after the climate models?
Well, actually, I have a use for the models. There's no way that models can accurately, well, there is a way maybe, simulate fluids. I mean, the trouble is our atmosphere, our ocean, have motions on every scale. They have motions on the scale of your fingernail. They have motions on the scale of the planet. They all have an impact. The small-scale turbulence in the boundary layer, the clouds, which have a scale of a kilometer or so, the weather patterns that have scales of thousands of kilometers, and you're modeling them on a computer. And even today's massive computers can't resolve a centimeter. That would be incredible. So they have to assume what the small-scale turbulence does. They have to assume what the clouds do. They have to assume what, all sorts of things are doing. And even then, there are some systems where you can prove mathematically that as you reduce the mesh size over which you're approximating things, because you're not doing it continuously, you have to just make points, that it converges to the right answer. But no one has ever done that for fluid dynamics. We don't know if it even converges. So you have to, in these models, put in, often you'll run a model and it goes haywire. You throw in damping to prevent it from going haywire. The damping has no physical basis. It's just to keep the model from blowing up. You're doing all these things, and you're hopeful that it may still have some insight. Now, I said, I actually am not against models. So, for instance, if you do theory for a phenomenon in the atmosphere, you usually do what's called order of magnitude analysis. What that means is you take the full equations and you try to estimate how big and small the terms are. And you try to see if these terms are small, can I approximate the system with a simpler system? And can I test it in this way? And you learn a lot from that. Almost everything we know came from that sort of analysis, not from models. But once in a while, if things get complicated, I'd like to look at a model and see whether there were things possibly going on in the model that might go on in nature that I hadn't thought about. And so the models can be useful promoters of more thinking about possibilities.
Sure, of course. of course, that's very different than assuming that they're valid models of what's going to happen with
Of course.
the real climate.
And
so, okay, I've two questions on that front. Is it hard to approximate fluid dynamics regardless of mesh size because a fluid system has so many degrees of freedom?
It's very hard to do. I mean, nobody would pretend. Let's say you have a gurgling brook with pebbles and so on, and it's doing all sorts of things. Nobody's going to predict the eddy for, let's say, a mile. I mean, that would be hopeless. You might make a statistical forecast on certain things, and you might get useful information, and you might be able to make an approximation that tells you how the roughness of the surface affected the flow rate and so on. But and you know, all you do is scale that up many orders of magnitude, and you have the Earth's atmosphere and those little eddies that you couldn't track are now your weather systems and so on. You still have trouble tracking them.
Well, so part of the issue here is that we're dealing with temperature changes that are of relatively small magnitude compared to the potential range of temperature change. And what that means is that for that degree of accuracy in prediction, let's say you need an accuracy of 1 to 3 degrees over 100 years, you have to have an unbelievably finely tuned model at an extremely high level of resolution. And then with the difficulties in modeling fluid dynamics, it isn't even obvious that you could do it in principle.
I think that's probably true. You can restrict, as I say, you damp the models, you keep them from blowing up, you do all sorts of things. And, for instance, with the greenhouse picture, I've been critical of it because I think it only really is useful in the tropics. But it is useful if I'm comparing Venus and Mars and Mercury. For them, the gross idea of the greenhouse does tell you why they're different. But, the changes in the Earth's climate involve minuscule temperature changes compared to the temperature differences between the planets.
Right. Well, then we have the additional problem on the political front so imagine you have an unstable climate model or an inaccurate climate model at the scale of resolution we're discussing. And then you put on top of that an economic model. And the economic model uses the climate model as an axiom, and then it tries to predict out 100 years, which I just don't see that as going anywhere at all, because you can't predict economic development with any degree of accuracy over a 100-year period. If you could do that, you'd have all the money in the world almost immediately if you could generate a model that accurate. You simply can't do it.
No.
So if you stack a bad economic model on a flawed climate model, you really do have a Tower of Babel.
Well, and they don't even do that. I mean, the economic models that people like Nordhaus and so on use just take that metric for climate and assign...
Right, but they assume it's accurate.
And they assume that you can put a monetary value on it.
Yeah.
And then, tune the... there are various kinds of models that do these things, but I don't know what to say. I mean, I don't think any longer that it is the models that are driving the perception. I think it is the pure repetition. And this was understood from the beginning. In 1988, when Jim Hansen gave testimony to the Senate about finding that there was global warming. And Newsweek had a cover. And the cover showed the Earth on fire and had the label, "All scientists agree."
Right.
Now, you had all sorts of funny problems at that time. Like most weathermen disagreed. And the American Meteorological Society decided they needed re-education. I mean, the march through the institutions was pretty effective. And we could talk about that. I mean, that's been...
Well, let's talk about this, because I was going to push back at you again, playing devil's advocate. So we hear all the time this idea that, 97% of scientists agree that climate change is real, which is different than saying that global warming is real, by the way. But 97% of scientists agree. And now we're hearing from Dr. Richard Lindzen, and he doesn't agree, but 97% of scientists do, so why the hell should we listen to Dr. Lindzen? And so let's start with the 97% of scientists agree claim.
Well, yeah, I mean, there are a couple of aspects to it. There are some studies, like one by a man called Cook, that were just bogus. They, ended up looking at 50 papers, specially selected, and found, this percentage. And this was taken apart in the Wall Street Journal by Spencer and Bast, and it was nonsense. But there are some issues where I think you could say there was 100% agreement. So, for instance, if you were to say CO2 is a greenhouse gas, and adding it will probably create some warming. I don't think too many people would disagree. I think the only thing would be how much, and many people would think it would be negligible, but no one would disagree with that. And so, given this telephone game, where you can say something perfectly innocent, and the politicians can interpret it as saying, oh, so you agree that we'll have warming. And that warming, however small, they'll assume is the end of the world. Well, yeah, there's agreement. But It's not agreement with what they're ultimately claiming, that it's an existential threat. I think if you've posed it that way, you would, for instance, notice that the UN's IPCC, Intergovernmental Panel on Climate Change, never in its working group 1, which is the only part dealing with science, speaks of an existential threat.
Right. Well, Lomborg has been telling people that constantly.
Yeah.
He's with his attempts to shed some intelligent light on this issue. He keeps saying, well, look, I'm willing to accept the IPCC forecast, even though he has some problems with the forecast. He said, look, I'll give you that, but the negative consequences that are often assumed are simply not realistic.
Even there, I mean, in the part I participated in, we said that, the models cannot handle water vapor and clouds, and thus there is no basis for our assertions about the feedbacks. That was in there.
Mm-hmm.
And it was interesting because, the whole procedure is a little bit nutty. I was responsible with 2 other people for 3 pages. For this, we traveled around the world twice or 3 times. The meetings, and you had, quote, thousands of the world's leading climate scientists, which is a field that probably had a few dozen, early in my career. Mm-hmm. And suddenly, when you piled in the money, in the US, I think the increase with Clinton Gore was maybe a factor of 15. You suddenly had thousands of, quote, climate scientists. Now, no one in my department claimed they were a climate scientist in 1990. Because, nobody, I didn't know everything about, paleoclimate. I didn't know how you assessed ice cores. I knew dynamics. I knew radiation. Other people knew other things.
Right.
But
it's not a field of specialization, climate science.
Right. It is the definitive interdisciplinary thing, and nobody has mastered all the disciplines. Trouble is, when you increase the funding 15, and the condition for funding was supporting the narrative, that you then could get lots of people, all of them calling themselves climate scientists, and most of whom have not familiarized themselves with the physics and the chemistry and so on. So you have this idiocy of impacts. So, you've seen it, global warming and obesity, global warming and diabetes. I mean, anyone can get a piece of the action.
Well, what happened to you on the funding front when you started to, let's say, swim against the tide to some degree? Although really what you were doing was just pursuing your research.
For a while, I would say in the 90s, I continued to get money from the National Science Foundation, but never for climate. I was working on hydrodynamic instability, other things that were pure meteorological. But by the 90s, late 90s, I was known well enough for my skepticism of climate that people were rejecting it, saying, he'll use some of this money for that. NASA also was pretty open in the 90s. And so, for instance, my work on feedbacks, my colleagues were from NASA. And it was okay. But by the end, there was a NASA administrator who was skeptical of climate, and they got rid of him. And they got stricter. The Department of Energy was actually trying to keep balanced funding, and then the government just clamped down on them. And so
that also means that, so that's very interesting too, because it means that not only does the narrative spin itself up to chase the funding, but any elements that would run contrary to the narrative just vanish.
Oh, yeah. I mean, at MIT, for instance, we had a celebration of the work of two distinguished faculty members who had died some years ago. This Jewel Charney and Ed Lorenz, chaos theory and so on. And, because of my closeness to Jewel, they asked me to speak on that. And the administration from MIT decided, no, given his position on climate and that we have a climate initiative, we can't do that. The department was quite okay. They found someone else to give that talk, and I gave another talk, and so be it. But the administration was upset with that. It again, I mean, now...
Well, it's really appalling to hear of that sort of thing happening at MIT. I mean, I'm always hoping that the engineers and the STEM types will have enough, what would you say, clout and political conviction to push back against this hyper-administrative invasion of the technical schools and the universities.
How should I say?
It happens at MIT. You have to think things are very, very sad. That's very, very sad state of affairs.
Hope springs eternal, but we just went through the issue of Dorian Abbott. I don't know if you heard about it.
Yeah. Oh, yes. Yeah, I know Dorian.
He was going to give a talk on exoplanets. He's keeping away from this issue in a way. Exoplanets is easy. But on the other hand, he had written a piece with someone from Stanford for Newsweek, in which he said, they really didn't think diversity, equity, and inclusion was that great. They preferred maintaining meritocracy while having school choice for children, including poor children, black children, so that they could be qualified for equity, instead of it being a kind of trap. And so MIT's administration decided that this was not consistent with MIT's values.
Yeah.
And, a statement, and, then it got the point, who speaks for our values? And
that is the question, all right.
And, this is very much the case with almost every university, every professional society, and you probably know this. Yeah. The people in the faculty, the people in professional societies, are busy. They like their work. They're doing things they like. And so you often choose one person to be executive director or so on, and they're happy not to have to do it, or to be president of a university or a dean. Not everyone wants to do it. They'd rather do their science, their research, and so on.
Their research, yeah. Well, that's a big problem because it leaves the administrative avenue open, eh?
And they can speak for you and speak of our values without ever polling you. And that's true in the professional societies. It's true of the National Academy in the U.S. There are a handful of people who can speak for the organization, and the organization is full of people who would rather do their work and happy to leave them that power.
Yeah. So what's been your experience with cancellation? You said it got harder and harder for you to get grants, so that's definitely a problem when you're trying to run a lab at MIT.
It also makes it almost impossible to publish. As I say, editors get fired if you get published. The more common thing is, among the peer reviewers, they insist that there be gatekeepers. So you'll send in a paper, and a lot of people have had exactly this experience. At first, it was pretty crude. So one of the papers I published in the early 90s, I had submitted to Science, pointing out questions about climate. And they sent it back without review, saying there's no interest in this.
Oh, yeah, right. Oh,
okay.
Yes. Mm-hmm.
But then...
No interest.
Right. And then they got a little bit more, I don't know if I'd call it sophisticated. You would send it to a journal, and they would reject it immediately. Some good. And then it came, that wasn't very effective because you'd send it to another journal. So what happened is you typically, and again, this is a common experience, you send it to a journal. They take about 6-7 months to review, and they send back a review that says accepted with major revision. And so you spend 6 months making major revisions, if you pay attention to them, send it back, they take another 6-7 months and reject it. That got them to stymie it for a year, so that you're not sending it to other journals.
Right. Well, it's also a very good way of wasting the time
of people
who might be actually trying to conduct research.
Right. So, all these things happen. And even with my students, I couldn't tell them, to oppose global warming. It would ruin their careers. They couldn't even get a foot in the door.
Well, was being associated with you eventually, was that enough to make it difficult for your students to get a job?
No, I don't think so.
Well, that's good. That's good.
I
would have expected that to have happened.
No, I hadn't seen it happen. But, I think most of my students, I think all of them pretty much, have steered clear of climate. There are other things you can work on, just like with Dorian. I mean, he doesn't want to get in trouble with climate. Pick an area which isn't climate. The only difficulty with it is funding imbalance can give preference to climate. On the other hand, they've induced so many people to support climate alarm that they probably don't have enough money to support all of the people who want to go feed at the trough.
Well, the other problem, of course, is that the very people who are hell-bent on pursuing their actual research, that's where all the real scientists are. And so now if we're in a situation where the real scientists, and those would be the ones who want to do their research, are refusing to have anything to do with so-called climate science, then what happens is that we're deprived of the very expert voices that we would need to bring some sense and stability to the overarching narrative upon which so many of our economic decisions are made now. So that just doesn't seem like a very good state of affairs.
It's not a good state of affairs, but it's desired by the people who want this state of affairs.
Right. Well, so let me recapitulate, because we're running out of time on this section. So we talked about your career and where you worked, MIT and at Harvard, primarily on the academic front. We talked about the fundamental climate narrative, which is that, well, climate's a major concern. It's changing primarily because of the greenhouse effect. That's a consequence of carbon dioxide. Most of that's warming. There are a variety of potential runaway positive feedback loops involved. You're not convinced of any of those propositions, that climate should be our major concern, that the greenhouse effect, as popularly conceptualized, is an existential catastrophe, that carbon dioxide is a contributor, again, of existential proportions, or that the positive feedback loops that are often put before us are likely to manifest themselves. In fact, you think that the climate system has enough degrees of freedom to be relatively immune to large-scale perturbations. Yes? Is that a decent summary?
Yeah, I mean, I'd modify it a little bit. I think feedbacks and tipping points are slightly different, and you're conflating them. I don't think this system has tipping points. It has feedbacks.
Right. Okay. Well, that's the critical issues.
But they're not runaway
there's feedback loops in it. Yes. Okay. So it's the tip. Okay. I'll make sure that I use that terminology from here on in. And then we talked about we tried to investigate some of the reasons why this more apocalyptic narrative has gained a foothold. We talked about the Malthusians. We talked about the political tilt of the funding regime. We talked a little bit more implicitly about the fact that more apocalyptic and doomsaying prognostications tend to attract a lot more attention, and so that's a big problem.
Constant repetition, and the fact that children, Al Gore, it was John Kerry who made this statement. I mean, it was just astounding. I think it was at a talk in Indonesia. He said something to the effect that we all know how difficult physics and chemistry can be, but climate is easy enough for any child to understand.
Right. Which showed you the level of his understanding.
Well, yeah, but also the impact is we're starting to teach kindergarten children climate.
Yeah.
But you don't teach them
and
science.
Terrifying them.
Yeah, right. Your world is coming to an end in 10 years unless your parents stop eating meat or, God knows what.
Right, or driving their vehicle or heating their house to keep grandma warm.
Or recharging their electric car.
Well, that too. Yeah. All right, so let me offer a set of propositions to the listeners and stop me or clarify what I'm saying if I get it wrong. So there are lots of drivers of climate variation. The big drivers have to do with oscillations in planetary orbit,
or other
comparative effect of, or other factors.
Yeah, there are so many factors that would impact it. There are ocean currents. For instance, again, it's a technical term, but the surface of the Earth is not isolated. It's not in equilibrium with space. It has the oceans underneath it. Ocean circulations have timescales up to 1,000 years, and they're constantly bringing fluid up and taking fluid away from the surface, and that fluid is carrying heat. And so the system is never quite in equilibrium. It varies on its own. Until we understand these systems perfectly well, we don't necessarily have a good theory for the fact that, there was a medieval warm period, there was evidence of a warm period, 2,000 years ago, all sorts of things. There were things, oddly enough, let's say at the beginning of the 19th century in New England, every town had a learned society, and they had their proceedings. And you would look at these old documents of ordinary people, well, ordinary educated people at that time, discussing whether Rome, when they had vineyards and so on, was warmer than it is at their time. They're still in the Little Ice Age. And they were wondering if it was just reportage or there was something really different. Had climate changed? They were doing sophisticated thinking about it, which has virtually disappeared from our world.
We also talked about the 97% of scientists fallacy, and you pointed out that 97% of scientists likely agree that carbon dioxide plays a role in greenhouse warming phenomenon.
Yeah.
But that doesn't mean that 97% of scientists believe that there are tipping points built into the climate and that we're going to slide off the edge of an abyss within the next 100 years.
Oh, no.
Those are very different claims.
No, and it's, as I say, I mean, I was speaking at a group, I think, Doctors for Disaster Preparedness, and they'd give me some recognition, and I decided that I would point out who opposed this narrative during the early 90s or the 90s. And it was leading figures in the field. And Bill Nye, the science man on TV or something, was saying that, these are just old people who, they'll die soon and we won't have these objections. And there was some truth to that. I mean, you had directors of major labs, directors of the Max Planck, people who are heading the European Medium Range Weather Forecasting, which is a premier group, all of them objecting to it. Presidents of the National Academy, and so on. But starting in the 90s with the takeover of major funding institutions and so on, you weren't going to get many younger people.
Right. Okay, so if we close this off, and maybe we could do this, maybe you could take 30 seconds, and we'll get a lot of relatively young people watching this YouTube channel, and they're worried because they've been fed a non-ending diet of apocalyptic catastrophe and oppressive patriarchy since they were like 3. And so if you wanted to address them directly and say what you wanted to say about what we can expect over the next 50 years, let's say, because that's kind of not a bad lifespan viewpoint, or 75 years, what do you think, what should we be contemplating on the climate front?
Much the same as we've seen. You'll see variations. They've always occurred. There will be places like the Gulf Coast of the U.S., which had been a citrus country in the 40s and now is too cold for citrus. Other things will change. Things always change a bit. There may be, several inches of sea level rise, but not a lot more. There's no evidence it'll be much more. You'll still have a situation where if you live in New England, Mark Twain's remark, wait a minute and the weather will change, will still be true. And, that's life. That's why you have overcoats and gloves and swimsuits. And there'll be nothing special. It's not cataclysmic. You're not going to be inundated with hungry polar bears fleeing the Arctic. You're not going to have cities underwater. And, get on with your life. But the question is, if your teacher insists on your saying the world is coming to an end or you won't get promoted, I'm not sure what I should tell them.
Well, I've told my students my whole life, I said, never, you don't falsify your words. Because the thing is, I'll tell you an experiment, a psychological experiment that's quite interesting. It might even be valid. So imagine you bring people in to the lab, young people, and you give them a political attitudes questionnaire regarding their views on a particular topic, maybe abortion, maybe climate, whatever, some topic that's, relatively contentious. And then you have them sit down and write a 500-word essay arguing against their position. Now, they know they're doing this in a lab. Then you bring them in a week later and you give them the same political attitudes questionnaire. You find that their attitudes have shifted substantially and significantly towards the direction of their writing. And so the problem is you can't falsify your words without falsifying your perception. Because your words construct your perceptions. And so if you kowtow to the teacher's ideology, we found this too when we were looking at what predicted politically correct beliefs. So the trait agreeableness did, being female did, having a lower verbal IQ did, but another major predictor was whether or not you'd taken any courses at all that were explicitly politically correct in their orientation. So you have to be very careful about kowtowing to the ideology because you can't get away with it. You'll falsify your own psyche if you falsify your words.
I think I agree with what you're saying, but 1984, was a fairly good example of how society can break that down.
Yeah.
And so
you've maintained your ground. How come?
Age. In other words, it's the business that for scientists of an older generation, up to mine, pretty much, maybe a little further, we could develop our reputations, our work product over a freer time.
Yeah.
The other thing is theoreticians don't need as much money as experimenters. And so I needed money just to support students. I didn't need equipment. I didn't need very much of anything else.
Right.
But it was mainly that people were advanced in their career. If you were director of a lab and so on, if you were near retirement, you could speak freely. The more sad were the weathermen, the people, the media forecasters and so on, who had a love of meteorology in many cases, were very knowledgeable, and objected to this by and large. I would go on a train ride or something, and meteorologists from the media would see me in there and say, "Thank you for that." But the media have been firing people who don't attribute every weather event to climate.
Right.
And the meteorologists know this is nonsense, but they just, are being pressured immensely. And we were lucky. Our jobs were not at issue. We had tenure and so on.
Yeah.
But younger people don't have that luxury.
Yeah. Well, and being canceled is no fun. I mean, I've known like 200 people who've been canceled, and it's about equivalent to a major illness. It's no joke. So, all right, sir. Well, look, for everybody who's been watching and listening on YouTube, thank you very much for your time and attention. And Dr. Lindzen, thank you very much for your calm and dispassionate and kind, I would say, analysis of the current situation, and for agreeing to speak to me today and to be providing all the people who are watching and listening with the fruits of your decades of labor. And I'm going to talk to Dr. Lindzen for another half an hour on the Daily Wire Plus platform, by the way, probably on a more biographical front. I'm interested in how his career developed.